Hi everyone, this is Nafish. Today we are going to go over Chebyshev filter design. So we are going to focus on the digital filter. As you know, like there is also an analog part of the Chebyshev filter design, but in today's lecture we are going to go over the digital filter design. Okay, and there is also type 1 and type 2 Chebyshev filter. Type 1, which has ripple in the passband, but it has like steeper roll off. Okay. On the other hand, in type 2 there is no ripple in the passband, so basically there is no amplitude fluctuations when a signal is passing through the filter. Okay, however the cutoff frequency is not as steep as the type 1. Okay, so there is some trade-off there, but we are going to see both of these filters implemented in Python today. Okay, basically I have imported this Scipy library as SP, right? You can see here. We also have NumPy and Matplotlib for plotting purpose. Okay, so let's get started. First of all, the idea here is, I'm just going to show you how we can denoise or remove the noise from a signal using this Chebyshev filter, and also then look into the detail of this filter, like the ripple, then the order, and also the types. Okay, so let's get started. First of all, we have to create a noisy signal. Okay, and I'm selecting a sinusoidal wave to create this noisy signal. Okay, so let's say we're going to create some noisy signal right here, and our signal is SIG is equals, we have the amplitude, and then we have to import this sine function from the NumPy library. Okay, so np.sine, and then inside that we have 2 times np.py times f times t. It's kind of very familiar equation. This is equation for the sinusoidal wave. Okay, so what are the parameters is not defined. Let's say our amplitude is 1, just taking a normalized amplitude, and then we have to define frequency. So frequency f is, let's say, 100 hertz. Okay, and now from there we have to define this time vector t. But to define the time vector t, we need to have the sampling frequency. Let's say our sampling frequency fs is 10 times our frequency, which is 100 hertz. Okay, and maybe we can take more than that, let's say 20 times. Okay, and then we need to have the samples. How many samples we have in the signal? We can say, let's say we have 500 samples. So now we can define this time vector t. So np dot a range, then samples. Okay, and that's going to be divided by the sampling frequency. So our signal is going to have this many samples, okay, within this time period t. Okay, and also we can plot the signal. So plt dot plot, we have t in the x-axis, and then our signal sig. Okay, and let's plot out the signal first. So this is our sinusoidal wave. Now we are going to do two things. We are going to add some noise with this signal. Okay, so sig with noise. Okay, so I'm just taking this signal right here, sig, plus adding noise. Okay, some random noise. So np dot random dot normal, and then let's say the distribution is 0 mean, 0.5 standard deviation, and then the size is np dot size of our original signal without the noise. Okay, so you can see in this step we are adding noise with this signal np.random normal, and then we are just defining the distribution of the noise. We can change these parameters to introduce more randomness and more noisiness in the signal. Okay, so let's plot this signal as well, and I'm just going to have signal with noise. Okay, so let's plot it, and you can see you can barely see this the sine wave. Okay, it's kind of very much noisy now. Okay, and our original signal is kind of rarely visible due to this noise. Okay, so our next job is to remove this noise, okay, and get back to the original signal. Okay, I just wanted to do something here, plt dot figure. Okay, and then we had to have fixed size. So basically we wanted to extend this plot on the horizontal direction. So let's say 12 and 4. Okay, so extending it right in this direction. Okay, so plot it. Okay, so this looks more clear, and you can see how much distorted the signal is. And now we are going to use this Chebyshev filter to remove this noise. Okay, so right now I'm using type 1 Chebyshev filter. Okay, first let's remove this noise, and then we will dig into type 1, type 2, and different filter parameters. So the way we can call this Chebyshev filter from the Scipy library is, we already defined the Scipy library as SP, right? So SP dot in the signal, if you press tab, you have all these options. Okay, so just press C, and you can see Chebyshev right here, type 1. You also have type 2. Okay, so we are going to have type 1 right now, and then let's define the filter parameters. First of all, the order of the filter. Okay, and then comes the ripple, and we are going to define all of this. Okay, but let's maintain the order. So first, the order of this filter, then how much ripple we're allowing in the pass band. Okay, so these are the design parameters. Okay, and now what is our cutoff frequency. Okay, next parameter is what's the filter type. So let's say we are going to have a low pass filter, right? And then the next thing is the sampling frequency. I think we already defined the sampling frequency, so I'm just saying like fs, sampling frequency, is equals to fs because it's already defined. Okay, and now the last two is whether it's oops, I think it's called analog, but some reason it's not popping up, but let's write it down. So analog is equals to false. Okay, so because we are defining a digital filter, right? And the last parameter, but the most important, is the output type. Okay, so we are going to have as an output type of SOS. Okay, now I haven't talked about this SOS, but let's write it down. Is SOS is second order section. Second order section. Now let's get a little bit deep into this SOS function. Okay, so you can see we have order here, right? Here, right? So what is the filter order? And this is the design parameter, and we can change this order and can try to see how it is impacting the filter. But as a starter, let's say n is equals to 5. Okay, so this SOS second order section means if n is equals to 5, we can write down this filter as 2 plus 2. So two second order filters, right? One second order filter right here. This is the second one, and then one first order filter right here. So we can break down the filter in smaller filters. Okay, in that way we can have more accuracy and more preciseness. Okay, so that's why we are wanting to have this output as second order filter, because this is a high order filter, right? Because sometimes we might have, like, let's say 7. Okay, so rather than having a whole filter, you can just break it down into 2 plus 2 plus 2 right here, and then a single order filter with real coefficient. Okay, so just think of a second order section is just like smaller section of filters. Okay, with 2 poles and 2 zeros. I'm coming into that. Okay, and basically this order you can break it down. Okay, so this parameter, let's say SOS, is equals to this, and let's look into the values. Okay, so I'm going to run it now. This sorry, these things are not defined, ripple, and I was excited so I couldn't define it. So let's say our ripple, let's say ripple is 3 dB, meaning when the signal is passing the filter, we can allow up to 3 dB amplitude fluctuation. Okay, or in other words, some attenuation. Okay, so let's define it as 3 for now, and this cutoff frequency fc is f. We already defined the frequency right here, which is 100 hertz. Okay, and I think we are all set, so we can run it. And now let's look into the SOS parameters. But before we get into that, let's imagine how many what is the size of this SOS. Okay, so you see we have 1 2 3 4 filters. Okay, so let's run it. Oops, to run this one. Okay, and np dot size of SOS. Okay, so we have 24 components. Okay, component is like the numerator and denominator coming into that. And what is the size, or sorry, what is the shape? 4 and 6. So you see, we already said there are 4 filters here. 1 2 3 3 second order filter, 1 first order filter. Let's say if we have let's say if we have 9 right here. Okay, then how many filters we're going to get? Imagine we are going to have 2 more right here. Okay, right here. So 1 2 3 4 5 filters. Okay, let's run it, run it. So you see 5 filters right here, and this 6 is the filter parameters. Okay, and now let's get into that. I have a Wikipedia page open right here, and you can see this second order section. You can go into digital bicot filter, this Wikipedia page, and you see we have 6 right here. So 5 is the number of filter, and 6, what is the 6? So 6 is nothing but the numerator and the denominator right here. So 1 2 3 1 2 3, total 6. So the b and a parameters of this transfer function. So we can always represent a filter as a transfer function, right? And this one right here, you can see it gives us the transfer function right here. This b1, b2. So we have 3 numerators and 3 denominators, 6 total components. So if you look into this, okay, we have the number of filter is 5, and each filter has 6 components. So total the size is 30. So that's how we got these values right here, okay? And this is what this SOS represents, okay? So if you are more interested, you can get into this Wikipedia page and get some more insight from that. But I think for this explanation, I think we are almost done here. So we have this SOS, and now we can filter this. So SOS is nothing but we have the B and A component, like the numerator and denominator component of the transfer function of this nth order filter. Okay, so now it's very easy. Filtered signal is nothing but np dot sos. Okay, sorry, should be scipy dot signal, and then source field right here. Okay, and now here is also another catch. I will just show you here. But if you import this source field right here from the signal library, then you have to pass SOS, and then the signal you are going to. So I'm passing these B and A parameters, or this filter coefficient. Okay, and then we want to filter the signal with noise. I'm just passing our signal to be filtered. Okay, so this is the filter coefficient SOS, and then the signal to be filtered. Okay, and now we can just have a plot. So plt dot plot, and then we have in the time axis, and then we have the filtered signal. Okay, right here, and we would like to plot it on top of this original signal. So let's say we have t, and then we have signal with noise right here, and let's also extend this a bit, so so that we can have wider view. So I can just say like this. Okay, so let's run it. And so this is this orange one. You can see this is our filtered signal, and this was our noisy signal. Now what you can say from this filtered signal, these filter signals look really good. There is no noise, but there are a couple of catches, couple of things you have to focus. One is it is kind of attenuated. Okay, so we had 3 dB ripple. Okay, so that means, like, we are kind of attenuating the signal. The amplitude is kind of getting distorted, okay, by this much amount. You can, if you increase the value, let's say we are going to have 5 dB attenuation, is going to be more distorted. Let's run it, and you can see the amplitude, it's reduced. But on the other hand, you are going to get a sharper cutoff, and we are going to go over all this. Okay, but now you can see another catch here is the starting position here. You can see the original signal was starting right here at time 0, but the filtered signal, there is a time delay. You can notice it. Okay, so definitely there is a time delay. So this is really, it's a normal thing. Whenever you are applying filter and you are filtering a signal, and the higher the order is, the more delay you are going to get. So if I reduce this to order 3, okay, then you can see the signal, it is little bit closer to the starting position. You can see minimum delay now. So the delay is kind of reduced by reducing the order. Okay, however, this is a kind of practical case. Whenever you are going to use a signal, you can see some delay. So using a filter will always introduce some delay. But there is another parameter called source field right here. You can see, so basically this will take away that effect, the delay effect. So basically, you are filtering a signal in forward direction, and then it's going to do the same thing in the reverse direction. So basically nullifying the delay effect. You can use this one as well if you want to keep it aligned with the original signal. So if I do that, you can see it's kind of pretty much on top of each other if I use this source field. Okay, now ripple, let's reduce the ripple a bit. So let's say ripple is equals to 1, and you can see our amplitude is kind of catching up the blue line. Okay, so you can see we can pretty much get away from all these noises by using this Chebyshev filter. Okay, but this example was, to understand the filter a bit more, okay, rather than denoising this signal. So you can already see it two parameters, this ripple and this order, how they are impacting this signal right here. Okay, and then we are going to play more with this in the next one. So basically, what I'm going to do, I'm going to copy this whole section from here, and let's look into the response of the filter. Okay, now we know, like, hey, Chebyshev filter can do this filtering and all these things, but let's dig into more into some other parameters. Okay, and I'm going to run a for loop now. And so let's say we are going to have different ripple. So ripple, let's say 1 2, let's say 1 3 and 5. Okay, and let's run a for loop right here. So for I in ripple. Okay, so I'm running a for loop here, SOS filtered signal, and then going to plot it right here. And here I'm just going to plot this filtered signal altogether. Okay, not the original signal, and just wanted to show you again the ripple, how that is going to impact the amplitude. So if I run that, and okay, so rather than doing this, what I can do is, let's label it. So label is equals to I. Okay, and pld dot grid on, and also pld dot legend. Okay, and let's remove this figure size right here from here and run it. Okay, so we have all these three signals all together, and they have different ripple, 1 dB, 3 dB, and 5 dB. And as I stated before, you can see the effect of the ripple, so kind of basically reducing the amplitude. However, it's going to give you the sharper cutoff, meaning it's going to leak the unwanted frequency less. Okay, so that's the positive sign. So now let's look into the response. Okay, so rather than having this output as SOS, we're going to have it as B and A, so numerator and denominator. Okay, and let's have B and A parameter here. So you are going to have the numerator and the denominator. Okay, and another thing is, like, whenever you are having this numerator and denominator as output, this frequency is going to be normalized to the digital frequency. You don't have to do anything, it's going to auto normalize it. Okay, and I'm going to show you the normalization factor later, but first plot this out. Okay, so we're going to have the numerator and the denominator, right? And we want to see the filter response this time. Okay, so here, rather than having these, let's call, um, I'm just going to get rid of this guy right here. Okay, so we have the B and A parameter, right, which is the numerator and the denominator, and we're going to get the frequency response. Okay, and also the filter response H, or the transfer function right here I just showed from this B and A component right here. What you need to do is call this sp dot signal dot, I think it's fix. Okay, so it's Z because we are in the digital domain. Okay, and this frequency is already normalized, as I mentioned, but I'm going to talk more about that later. But you know you are going to get the numerator and denominator, and you are going to pass it to this fixed function. So B and A. Okay, so basically this is going to give you two things. One is the x-axis, which is the frequency response, and H is the transfer function, or in other words, the filter response. Okay, so you have those two, and now plot it. So plot W right here, and then rather than this filter signal in y-axis, you're going to have this H. Okay, now you need to do two things. You have to convert it into logarithmic scale so that we can have a better representation. So let's say 20 times np dot log 10. Okay, and then take the absolute value of this H, because this is going to be a complex number, right? So I think we are all set on this part, but this W, this is in digital domain. This is in radians per sample. Okay, so this happened when we converted into B and A parameters, like the numerator and denominator of the transfer function. So when we're trying to plot it in the, we have to like we have to get out of this digital domain. Okay, so let's take out the normalization effect. Okay, so to do that, what you need to do is times fs, I think divided by 2 times np dot pi. So fs by 2, this is the Nyquist frequency, okay? Half of the sampling frequency. And that's how we normalize, okay? When we have the output as BA. And this np dot pi, this is the cycle in radian, okay? One cycle in the digital domain, okay? So I think we should be all set. Let's try to plot it and see. Okay, something is wrong here. I think I'm missing a rounded bracket somewhere. So 1, 2, 3, 4, 5, 6. Missing one right here. So let's plot it. Okay, so I think we got our filter response. I don't know, some. Oh, okay, because I haven't provided the legend here. So let's say label is equals to I. So it's going to plot all these 1, 3, and 5 ripples right here as legend. Okay, and also let's shrink out the x and y axis a bit. Okay, so that we can better visualize it. So x lim, let's say we have 0 to 500 hertz. Okay, and in y limit, let's say minus 70 dB to 0 dB. Okay, and let's plot it again. Oops, silly mistake here. So plt dot xlim and plt. Sorry about this. Okay. So it doesn't seem like it's falling in. Um, Maybe something is wrong here. 2 times np dot pi. Use a bracket just to avoid any issue. Let's use a bracket here. Okay, now it looks good. Sorry about that. I think that was I needed a rounded bracket there. But here you can see the higher order has steeper roll off. Okay, our cutoff frequency was 100, right? So you can see this roll off. Okay, so you are allowing more ripple, but your roll off is not as steep as this one. Let's change these parameters a bit. So rather than order um, 3, let's have ripple same. So let's have ripple as 3 dB, and then the order, let's or change the order. So let's say we have 3, 5, and 6 different orders. Okay, and this is ripple right here. So change back to ripple, and this is the variable now. And now plot it. Oops, some mistake again. Let me see. Order I for I in ripple. Okay, so for I in this order n. Okay, sorry. Okay, so here we go. So you can see this higher order is much more steep, but it has more ripple. I don't know whether you can see it or not, but let me shrink this x-axis a bit to 2, and this one is also to minus 30 dB. Okay, now I think it is clear. You can see the green one here. It has more ripple than compared to the blue one, which is only like 3 ripples should be, and then this one is 5 dB ripple right here. Okay, and this one the 6, the green one. Okay, so you can see like how the ripple and the order. Sorry, it's not ripple, it's the order, and how the order is kind of having an impact. Okay, now we talked about this type 1 filter. We can do type 2 as well right here. Rather than it's exactly same, we change this to Cheby 2. Okay, and all the parameters will be same. Okay, and now you can see the ripples will go away, but the roll off of this cutoff frequency is not going to be as steep as this Cheby one. Okay, so let's run it, and you can see right here. Although like I'm not comparing type 1 and type 2, but you can see the thing I wanted to show you. Maybe I can go up to 3 dB here. Right here. Okay. So now what you can see, just try to interpret what you see here. So basically there is no ripple in the pass band. Okay, we are very clear. Okay, however, if you look into the stop band right here, okay, there are some frequency leakage is going to happen. Okay, you can see like these ripples right here in the stop band, which is going to pass some unwanted frequency. Okay, so this is kind of like pluses and minuses of these two types of filter, but this is kind of very effective filter, as you can see, like how we were able to clear out the noise. So I believe like you can just play around with these parameters a bit and try to see how it looks like. Okay,